C3, A, B and C rates of reaction. Here we've got a table of values for two experiments, and we've got the time at 0 seconds, 5, 10, 15. Experiment A, we had start off with 0 centimeters cubed of gas given off. Then after 5 seconds there was 10 centimeters cubed. After 10 seconds we got 20, and it stayed at 20. Experiment B started again at 0, but didn't produce as much gas until it finally caught up at 15 seconds. So we can see that A went to completion at 20 at 10 seconds, whereas B took 15 seconds. So we can see that B was faster. While we're looking at that, let's look at some of the units. So if we're having a gas escaping, then the mass of a reaction vessel might go down. So the rate might be in grams per second. And if we are measuring the gas given off as we're doing in this one, the rates units will be centimeters cubed per second. Let's have a look at the graph that we might get from these results. So here we have gas evolved against time. Experiment A is this solid line, and it's steeper, showing that it's a faster reaction, and B is this dotted line, and it gets to the same point, but it's a more gentle slope. So steeper means faster. And over here we've got this very simple statement: if the reaction's faster, if it gives out energy in this reaction, the faster the reaction, the hotter it's going to be, or the more fizzy it would seem. The four things that are going to affect the rate of reaction: temperature. If the reactants are hot, the particles are going to be moving faster, they're going to collide more often and collide with more force, so we're going to get more collisions per second. If we increase the pressure of a gas, or the concentration of a solution, there are going to be more particles per unit volume, which once again will mean more collisions per second. If we use a catalyst will reduce the activation energy, so the reaction can take place at a lower temperature, which means it'll happen faster. But remember, the catalyst can be very small, and it will not be used up in the reaction. It must be there at the end or regenerated, so it's not actually part of the equation. And finally, we've got the surface area. If we've got a big surface area, and don't get them confused, big surface area means tiny little bits. So a powder has a big surface area, a block has a small surface area. Big surface areas mean you have more reactants in contact, so there are more particles touching each other, so there's going to be more chance of them reacting. And of course, powders, with them being more likely to react, are dangerous to store because they could explode or react very quickly.